Alright, in this video I'm going to be talking about the symmetry of functions and then further in the discussion about even and odd functions. So there are basically three types of symmetry that we are going to discuss. On the left here you can see a function that has y-axis symmetry. In other words, across this y-axis this function folds over perfectly. It reflects over that y-axis. If that's the case, a very formal definition of it is you replace the function, replace all the x values with negative x values, and you should get the original function back. It's not super clear, or it's not super easy to understand, I should say, so I'm going to show you some shortcuts to test that. But if a function has y-axis symmetry, we call it even. We call that an even function. If a function has origin symmetry, that means it reflects about the origin, so it sort of like rotates like 180 degrees here from like this quadrant 2 down to maybe quadrant 4. This is exactly the same as this. If that's the case, formally you replace the x's with negative x's and you should get the opposite of what you started with, and that function is called odd. The other type of symmetry is when you have x-axis symmetry, and x-axis symmetry has a different test and it's sort of a different look. So let's look at some very quick examples here. In the first one, top left, this function is kind of an interesting one. We're actually going to come back to that. Number 2 has what we call x-axis symmetry. This is an ellipse, and everything that is above the x-axis is the same as below the x-axis. Over here, this has y-axis symmetry. That is, of course, a parabola. Number 4 is a cubic function that has origin symmetry. Number 5 has x-axis symmetry. Number 6 doesn't have any symmetry. That's just a root function, looks like. Number 7, y-axis symmetry. Number 8 has origin symmetry, and number 9 doesn't have any of those types of symmetries. It is sort of symmetrical, and I guess the point of symmetry would be like 2, -3, and it's kind of an interesting one. Number 1 is a hyperbola, and that has symmetry across the y-axis. In other words, this whole thing, if you were to fold it over, you'd get this whole thing. And when I say fold it over, I mean you're folding over like this imaginary line. So it has y-axis symmetry. If you were to take this whole bottom section and fold it up across the x-axis, you would see that it folds perfectly on itself, so it has x-axis symmetry as well. And if you were to sort of rotate this thing 180, you would see that it has origin symmetry as well. So this has all three symmetries. A hyperbola does that. That has the center point there at the origin. Cool. So those are some examples. Now the tests. Let's get to the tests, the shortcut tests. If you want to test for symmetry about the y-axis, all you need to do is replace the x's with negative x's. And if you get the same thing at the end, then you have a symmetry across the y-axis. So let's see if this one works in our favor here. So let's test y equals x squared. If we ever start with f of x equals x squared, I just change it to y equals x squared. And to test to see if this thing is symmetric about the y-axis, which is right here, and we know that it is already, but let's test it. We're going to replace the x's with a negative x. Simplify. So here's our test. This is the point where we're testing. We're replacing the x's with negative x's and simplifying. So we get y is equal to positive x squared. Now, since that is exactly the same as what we started with, since those are the same, then this thing has y-axis symmetry this is an even function, and that means that it has y-axis symmetry. Alright, cool. So, I mean, graphically you can see that, 2 comma 4 resides right here, and negative 2 comma 4 resides right here. So, f of x is equal to f of negative x is what that means. 4 is equal to 4. F of negative 2 is equal to f of 2 is what that really is looking at. So anyway, the stuff in pink down here is more like the formal stuff. Over here is kind of like our shortcuts. So let's try the x-axis symmetry. The x-axis symmetry, in this case, you can tell that this is symmetrical about the x-axis. Let's test it though. So to test x-axis symmetry, we want to replace all of the y's with negative y's and simplify. And again, we get exactly what we started with. So we just compare those things. If they're the same, then we have x-axis symmetry. X-axis symmetry. Now that's not even a function if you think about it. There's, when x is 4, there are actually 2 y values, positive and negative 2. So that's not even a function, but it does have symmetry. It's kind of like it's a sideways parabola there. Now to test origin symmetry, we replace both y with negative y and x with negative x. And let's see what we get. So if we test this, negative y and then negative x to the thirds, and we're seeing if these are the same things. Well, negative x to the third is actually expanded out to be this. So it's negative y is equal to, let's see, positive x squared times negative x. That's negative x to the third. Both sides are negative, so let's make both sides positive. And what do you know? We've got this exactly the same as this. And when they are the same, we've replaced y with negative y, x with negative x, then we have an odd function that is symmetrical about the origin. So there you go. Those are your 3 tests. And again, more formally, if you're interested in that, you can say that when you replace the x's with negative x's, you get the opposite of the original function. That's, again, somewhat confusing, I think. If I were to teach it that way, I would not show you the shortcuts the way that I am, but I decided to just go with all the shortcuts instead, and I think in my experience as teaching this stuff, that's the easiest way for kids to learn. So, moving on. We're going to test this function for all the symmetries. So let's test first for y-axis symmetry. When we test for y-axis symmetry, the x's turn into negative x's. So we have our original function. I'm going to replace f of x with x. Excuse me. I'm going to replace f of x with y. Sorry. This and this mean the same thing, as you know. So I'm just going to do it like that. And then my test involves replacing all the x's with negative x's. And I'm going to see if I get the same exact thing that I started with. So this is the actual test right here. That's the replacement. So we know that a negative number to the 4th power is a positive number. A negative number to, again, an even power there is positive. So sure enough, we got exactly what we started with. Those are the same. So yes, f of x is symmetrical about the y-axis. In other words, this is even. This is an even function. Let's test, just to show you how it fails, let's test the x-axis symmetry as well and the origin symmetry. So I'm going to write my original down again. And to test x-axis symmetry, I'm going to replace my y's with negative y's. So negative y is equal to x to the fourth plus x squared plus x to the third. Solve it for y. That changes everything over here to negative. And when we take that out, what do you know? We have kind of an interesting thing here. We have y is equal to the opposite of what we started with. Well, that's not exactly what we're looking for. We want them to be exactly the same. So this does not have x-axis symmetry since they're not identical. And let's test the origin symmetry just to show you that test. The origin symmetry, the x's go to negative x's and the y's go to negative y's. I'm going to rewrite my original, which was x to the fourth plus x squared plus 3, I think. Yeah. And I'm just going to do replacements for both variables now. And let's see if we get the same thing. Negative y, that's positive x to the fourth, positive x squared plus 3. So this is going to be negative all of that. Oops, sorry, negative all of that stuff. So no, that does not equal exactly the same thing. So this does not possess origin symmetry either. It does have y-axis symmetry. This is an even function. And if you wanted to graph that, it might be a good idea. Let's put this into our graphing calculators and just confirm what it looks like. So I'm going to go into my calculator now, if I can pull it up here. It doesn't seem to be working right now. There it is. X to the fourth power plus x squared plus 3. Graph it. And I'm going to zoom out, zoom standard. And you can see that it does indeed have y-axis symmetry. So that confirms it for us. Let's go to the next example. And I'm going to test this one for symmetry as well. So here's my y-axis symmetry test. I'm going to replace all my x's with negative x's. Plus x minus x. And I'm just going to kind of simplify this. A negative number to an odd power stays negative. So those are all like that. If I pull a negative out of all that stuff, I am left with the opposite of the original. These are opposites of each other. They're not the same. So this does not have y-axis symmetry. If we test the x-axis symmetry, that means we replace the y with a negative and keep everything else the same. And we see that, let's get rid of the negative that changes all this stuff to negative. And again, that's not exactly what we started with, so it does not have x-axis symmetry. Let's test the origin symmetry. We replace both the y's with negative y's and the x's with negative x's. And we simplify it. Negative y is equal to negative x to the fifth minus x to the third minus x. Get rid of all the negatives. And what do you know? We're left with exactly what we started with. If they're exactly the same, then yes, we have origin symmetry, and this is called an odd function. And let's graph it to confirm. So I go back to my calculator and I put x to the fifth plus x to the third plus x. And I can see that I've got myself origin symmetry. First quadrant, third quadrant, rotated around 180. Cool. This one I already graphed. You can see that I have a sneaking suspicion that it has origin no, excuse me, it has y-axis symmetry. So I'm going to test that. So I'm going to replace all my x's with negative x's and see if everything fits together. Simplify this, and we're trying to see if it comes out to be exactly the same. Negative x to the second power is positive x squared. Negative x to the fourth power is positive x to the fourth, which is precisely what I started with. So yes, this is an even function. It has y-axis symmetry. And you can confirm that visually. You flip it over the y-axis, you get the same thing on the left and right. A couple more here. Got a function here. I have a suspicion that it has origin symmetry. So let's check it. Replace the x's and the y's with their negative versions. And we simplify. So negative y is equal to negative, remember negative x to the fifth power is negative x to the fifth power plus 2 times negative x to the third. I'm basically just getting rid of the parentheses. Minus minus, of course, is a plus minus 2x to the third. And I'll get rid of that negative out here. So I have minus x to the fifth plus 2x to the third. And what do you know? It's exactly the same as I started. So this is an odd function that has origin symmetry. In other words, everything is sort of spun around that point 0, 0. And let's try this one. We've got ourselves a function. I don't have a graph on this one, but I'm going to test. I'll just do all three tests really quickly. So let's do y-axis. So the x's go to negative x's. So y to the fourth plus negative x to the third minus 5 times negative x. Y to the fourth minus x to the third plus 5x. That's not what I started with at all. So that does not work. Let's test for x-axis symmetry. So the y's turn into negative y's. So I get negative y to the fourth plus x to the third minus 5x equals 0. A negative number to an even power it goes to positive. So yeah, this is precisely what I started with. So that is a yes. This has x-axis symmetry. And let's test the origin just for good measure. Change both the x's and the y's to their negatives and see if we get exactly what we started with. That's positive y to the fourth, negative x to the third, plus 5x equals 0. And you can see that that's not precisely what we started with. So there's an example of one that only has x-axis symmetry. And that has a weird graph. That looks like this. You can see that this is exactly the same as this. This is exactly the same as this. It's a weird one. That's tough to even put into your calculator. So in summary, those are your three tests. You know, there's a much more formal sort of reasoning for all this stuff, but I tend to see my students get bogged down in those formalities, and they really latch on to these three quick tests. And of course, as always, I think graphing utilities are really, really helpful. You saw me use my graph a bunch of times, so hopefully you're using your graphing calculators to your advantage, but you also have the ability to use algebra to confirm. So that was the video on symmetry and even odd. I hope you enjoyed it, and as always, hit subscribe so you don't miss any videos, and I'll see you in the next one. Thanks for watching.